Quinine is one of about 30 alkaloids found in cinchona bark, of which several have been found to be anti-malarial. Quinine is commonly used for the treatment of malaria and used as febrifuge. It is extracted from cinchona bark for commercial use. As you can see, there are a lot of optically active center. So this compound is optically active, and its specific rotation is about minus 158 degree, and have a bitter. It is a bitter solid which is insoluble in water. So let us move on to structure determination of quinine. As in case of any other organic compound, the structure determination of quinine also the first step of it is the determination of its molecular formula. Its molecular formula is C20H24N2O2. Okay, so we should know the nature of this nitrogen, that is whether it is primary, secondary or tertiary amine, then or it is whether it is NO2, etc. So by the reaction with methyl iodide, it forms diquaternary salts. That means both of these nitrogen are tertiary in nature. Okay. Then what about this O2? In order to find out this O2 may be in part of COOH group or maybe carbonyl or etc. So it is found that it is hydroxyl group. How it can be found out? It forms monoacetate with acetic anhydride or acetyl chloride. So it forms monoacetate. So since it forms monoacetate, it contains at least one OH. It contains only one OH group. So we should know whether it is primary, secondary or tertiary. For that, this alcohol is oxidized. When it is oxidized, it gives ketone. That means this alcohol is a secondary alcoholic group. So the second group is OH group. Then it is found that this quinine molecule, when heated with the HCl, it liberates one methyl chloride, CH3Cl, or chloromethane. Okay. So what is the indication? It indicates the presence of one methoxy group. That is, when methoxy group is hydrolyzed in presence of HCl, it forms this OH group is become free, and this Me will go with Cl and form chloromethane. So one of this oxygen will be a part of methoxy group. Then this quinine molecule is found to be unsaturated. That is, there is a double or triple bond may be there, but it adds one equivalent of bromine and absorb one molecule of hydrogen in presence of catalyst. That indicates the unsaturation is double bond. Then a double bond may be terminal or not terminal. So non-terminal. So it is found that the unsaturation in quinine is terminal double bond because it forms formic acid. That is, it contains this group CH double bond CH2 group. This on oxidation with KMNO4 under mild condition. So what happens? This bond will rupture and this part is converted into formic acid. Okay, so one of the oxidation product will be formic acid. So by the formation of formic acid under the oxidation with potassium permanganate under controlled condition indicate a presence of vinyl group. Okay, then In this quinine, we should have an idea. We have an idea already that the nitrogen present are tertiary. Then the functional groups are, one is OH group and the other is OMe group. Then there is a vinyl group is there. So in order to have an idea about the nature of ring or the skeleton of this molecule, this quinine molecule is first fused with KOH. The products was 6-methoxyquinoline and 4-methylquinoline. 6-methoxyquinoline. This is the structure of 6-methoxyquinoline. Here OMe. This is 6-methoxyquinoline. Then other product is this is nitrogen 4-methylquinoline. Numbering is like this: 1, 2, 3, 4, 5, 6. Okay. By the formation of these two compounds, we have an idea that this molecule may contain a quinoline ring as one part. So this is consider the structure of quinoline itself. There is 9 carbon atom, but here there is 20 carbon atoms. So the substituent in this ring will be very high, very big molecule. So for the actual structural elucidation of quinine, it will be very difficult. So this quinine is splitted into two compounds. That is, this quinine molecule is oxidized under controlled condition. It is oxidized under controlled condition to form quininic acid, C11H9NO3 and C9H15NO2. This is the name of this compound is quininic acid, and this compound is meroquinine. Meroquinine. Okay. So if we look at the molecular formula of this compound and this compound, here the total is 9 plus 11, 20 carbon are there. So by this controlled oxidation, actually this quinine molecule is split into two components, quininic acid and meroquinine. So by the combination of these two, we can have the structure of quinine. So next step is identification of this quininic acid and meroquinine. That is structure determination of this quininic acid and meroquinine.
Then the structural elucidation or characterization of quininic acid. Heating quininic acid with hydrochloric acid give another carboxylic acid, which when heated with soda lime yield 6-hydroxyquinoline. The structure of this 6-hydroxyquinoline is known at that time. That is, first we have heated with the HCl and this then heated with the soda lime. So we have an idea about the molecule may contain a 6-methoxyquinoline ring in this, and there is one more COOH. We don't know the exact position of this COOH group. That is why we are writing like this. Then when it is heated, this bond is hydrolyzed and it become OH. When it is again heated, the COH group is decarboxylated. That is, one molecule of carbon dioxide is eliminated and forms 6-methoxyquinoline. Similarly, when it is first decarboxylate using soda lime, it gives methoxyquinoline. When it is hydrolyzed and heated in presence of HCl, this bond again hydrolyzed to form corresponding OH group. So from these two experiment, it is shown that this molecule, that is, it have a quinoline nucleus and a COH group. So we should have an idea about the position of this COOH. This position of COOH or carboxylic group in quinoline was confirmed by further oxidation of quininic acid with chromic acid, which yield 6 pyridine 2,3,4 tricarboxylic acid, or quininic acid on oxidation with the chromic acid CrO3 in presence of H2SO4 gives COOH, COOH, COOH. That is 1, 2, 3, 4, 5, 6. 2, 3, 4 tricarboxylic acid. It is a 2, 3, 4 tricarboxylic pyridine 2, 3, 4 tricarboxylic acid. So, from this experiment, it is clear that the quininic acid have a this group, and if we check the formula of quininic acid, C11 H9NO3. So there is one more COOH group from this. Here it is CH3 group. Okay. So we should have an idea about where this COOH group is attached. So, in order to find out that this quininic acid is oxidized to this group, this indicate that this 2 COH will be as a result of a rupture of this bond. That is, here in actual structure, here is Me. Okay. This 2 COH is due to the oxidation of these two, and this COH is the COH of quininic acid. So from this, quininic acid is finally the attachment of COH group is find out by using this method. So we can conclude that the structure of quininic acid may be like this. That is, this COH will be attached here. Okay, this is the structure of quininic acid. The structure of quininic acid is confirmed by its synthesis. So the precursors are para-methoxyaniline and ethyl acetoacetate. So first of all, this NH2 group will attach or attack at here, and this molecule is eliminated and have a intermediate like this. Then when it is heated, it cyclizes, and then it is treated with the POCl3, and this OH group is replaced by this Cl. Then it is reduced, and this Cl is converted to H. Then it react with benzaldehyde in presence of zinc chloride. Here this O and 2 CH2 group is eliminated, and we have a double bond pH. Then it is oxidized, and this bond is ruptured, and this part will become the acid, and this part is removed. Okay, so the structure of quininic acid is obtained. So this structure and the previous structure is compared, and it is found that the structure of quininic acid is like this. After the characterization of quininic acid, we should know the structure of other component, that is meroquinone. So, meroquinine was found to be, its formula is C9H15NO2. So, we should know the nature of this nitrogen and this oxygen. In case of meroquinine, there is a carboxylic group. That is, it is confirmed that it forms monosodium salt. That is, only one COOH group is present, so that it forms monosodium salt. Then the nature of this nitrogen. It is found that this nitrogen is a secondary amino group. That is, it forms nitroso derivative and form monobenzoyl derivative. It is a characteristic reaction of NH. At least one NH bond is needed for forming nitroso derivative and form monobenzoyl derivative. That is, this group is replaced by COPH. So, in case of meroquinine, this nitrogen will be in secondary form. But we know that in quinine, both nitrogen in quinine are tertiary in nature. But in meroquinine, one of the tertiary nitrogen is converted into secondary form. Then the third functional group present in meroquinine is vinyl group. That is CH double bond CH2. We have identified this group in quinine also. So the vinyl group present in quinine was intact in meroquinine. Then, in order to have a number of skeleton or skeletal structure of this meroquinine, we have some more reactions. That is, heating meroquinine with HCl at 200 degrees Celsius. Before that, we have to know the double bond equivalent of this meroquinine. That is, here double bond equivalent is equal to A. A is 9 minus B by 2 plus C by 2 plus 1. That is 9 minus 7 plus 1, that is equal to 3 double bond. In case of 3 double bond, 1 is corresponding to this vinyl group, C double bond C group. 1 must be corresponding to this carboxyl group, carboxylic acid group, COH group, and the third one will be corresponding to the ring structure of the quinoline molecule. So in quinoline there will be a ring-like structure. Okay. So in order to have an idea about how many members are present in that ring, this reaction is done. That is, heating a meroquinine with HCl at 240 degrees Celsius gives 2-ethyl 4-methyl pyridine. This is the one. That is 3-ethyl 4-methyl pyridine. Similarly, on oxidation of quinoline with acidified potassium permanganate forms singoloiponic acid and formic acid. The structure of this compound is identified already, but the structure of this is new. That is that is why we are writing its molecular formula C8H13NO4 plus formic acid. That is one carbon less than this meroquinine. Okay. So then this oxidation product, that is singoloiponic acid, on further heating with sulfuric acid yield 4-methyl pyridine. By identifying this both these products, that is the 3-ethyl 4-methyl pyridine and the 4-methyl pyridine. It is common that here there is a 6-membered heterocyclic ring. The formation of pyridine derivative from meroquinine and its oxidation product confirm the presence of 6-membered ring containing nitrogen ring in meroquinine and in singoloiponic acid. So we have to know the structure of cincholoiponic acid and that of meroquinone. So the main structure is this pyridine unit. Then here there is 1, 2, 3, 4, 5. C5 is the. Then in meroquinine and cincholoiponic acid there is a COOH group. Okay, one group is COOH group. Then another group is CH double terminal alkene group. Okay, so 1, 2, 3, 4, 5. Five carbon is here. Then 4 more carbon should be there in case of meroquinine. So that 4 carbon should contain one COH group and CH double bond CH2 group. So there may be two combination. That is the point of attachment will be what at carbon 3 and 4, because we identified the product by using this this product. Okay, that is here the substituents are in 3 and 4 position. So the remaining 4 carbon should be attached at 3 or 4 and it should contain functional group COOH and CH double bond CH2. So there will be two types of combination, that is CH2 COOH and CH double bond CH2. Another combination is, this is one combination. Another combination is one COOH and CH2 CH double bond CH2. That is, from this product, the degradation product, it is clear that it have a 6-membered heterocyclic ring which contain a group attached at 3 and 4. So by remaining 4 carbon of this meroquinine should have a COOH group and CH double bond CH2 group. In order to satisfy that condition, there is two possibility. One is CH2COOH and other is CH2COOH and CH double bond CH2 and this combination. So we should find out what is the real combination. So for that, cincholoiponic acid is again reacted like this. That is, meroquinine is zinc distillated and we get cincholoipon, which on reaction with soda lime gives 3-ethyl 4-methyl pyridine. Okay. Then again it is distilled, then we get 3-ethyl 4-methyl pyridine. The formation of this compound 3-ethyl 4-methyl pyridine is evident that the substituent will be in 3 and 4 position. It is also confirmed by this reaction, that is it is present at that is this cincholoiponic acid. This is cincholoiponic acid. Sorry, this is meroquinine. Meroquinine also react with HCl2 and HCl and form 3-ethyl 4-methyl pyridine. Okay. So we should remember that by looking this structure, it is clear that the functional group we have mentioned two possibilities. Among that two possibility, the product will be one. That is the what was the two possibilities? CH2 CO OH and CH double bond CH2. Other possibility is COOH and CH2 CH double bond CH2. If this was the combination, the product after decarboxylation will be what? After decarboxylation will be, there will not be a ethyl group. Methyl group will not be present here. That is, if here is the COH group is present, then there will not be a CH3 group over here. Okay. So the combination will be CH2COOH and CH double bond CH2. This is the right one. So the structure of meroquinine, that is, this structure is also confirmed by synthesis. So now we are going to see the synthesis of meroquinine. Here the this nitrogen and sorry, this hydrogen and two molecule of this compound is reacting. That is, here one the Cl and one H is replacing, and two molecule of that reacts to form a secondary amine-like structure like this. And after hydrolysis, that is, this is acetal form. This on hydrolysis you will get aldehyde, but this aldehyde is very unstable and will undergo aldol condensation. That is, in case of aldol condensation, one hydrogen from here is removed as H plus, and the carbanion is formed. This carbanion will attack at this carbonyl carbon, and this will become OH, and this OH and adjacent H will eliminate to form a double bond, and there will be a CH2 group. Okay, so we will get a compound like this, and this will react with hydroxylamine and thionyl chloride to and replace the CHO group to CN. Then it will condense with diethyl malonate in presence of um, sodium hydroxide. Then we have this compound which on reaction with the barium chloride and HCl. That is, here also, here what happens, here hydrolysis is taking place and one carbon dioxide molecule is eliminated from here. Then this CN molecule is hydrolyzed to COOH. So we got this molecule. Then so by this method we have prepared plus or minus 5 loiponic, I'll write one more, 5 loiponic acid. Okay, what is the structural difference between this is plus or minus 5 loiponic acid. What is the structural difference between this 5-loiponic acid and meroquinine? This 5-loiponic acid is actually an oxidation product of meroquinine. That is, in case of meroquinine, instead of this COOH group, there is CH double bond CH2. Okay, I will write this structure once more. Okay. That is, the structure of 5-loiponic acid is like this. Here one H, then here one COOH, then here CH2 COOH. The structure, this is 5-loiponic acid. The structure of meroquinine will be what? NH. Instead of this COOH here, in case of meroquinine, there will be CH double bond CH2. This CH2COH I am writing like this. This is CH2, then COOH. Okay, this is the structure of what? Meroquinine. Okay, in order to we have noticed that there is no COOH group in what, in our original compound, that is quinine. Okay, we have seen that in both quininic acid and in miraquinin there is a COOH group. So this COH will come by the COH will be coming from the oxidation product of that is the point of attachment will be the COH group between these two molecules. So and also we have noticed that in case of quinine there is a tertiary amine group. In case of miraquine, in original quinine there is tertiary tertiary nitrogen, but in case of miraquine that is only secondary. So what will happen at the time of oxidation? This bond also ruptures. So the original compound, that is the original group, may have this group attached here. That is, I will write the structure of that compound. And sorry. Here CH double bond CH2. The name of this compound is 3-vinyl quinine. So the this group will be actually the branched chain of this quinine. Okay, this molecule on oxidation with chromic acid CrO3H2SO4 will rupture this bond. This bond is ruptured, and this is converted to COOH group, and this is NH. Then what is this compound? NH, here CH double bond CH2, here COOH. So this is the structure of miraquine. So original group will be this. Here this COH is coming because of the oxidation of quinine. Okay. Next, we should know what is the nature of functional group present at point of attachment of these two quininic acid and miraquine. So in first case, that is at first we have in preliminary analysis we have noticed the presence of a OH group. In neither the structure of quininic acid and nor miraquine, there is no OH group. So this OH group may be present at the point of junction between these two quininic acid part and miraquine part. The position of hydroxyl group in quinine was established by Rube et al. He oxidized quinine under mild condition to quinone. He oxidized quinine under mild condition, very mild condition. It gives quinone, which on treatment with amyl nitrite and hydrochloric acid yield quininic acid and N-oxide, which gave miraquine on hydrolysis. This transformation confirmed the presence of this COCH, this group. That is, quininic acid is containing C double bond O attached to a CH bond. That is why this H is replaced by this NO group in this reaction. Okay. So from this reaction, it is found that this C double bond O in quinone. This is the structure of quinone. Then this CH2, this CH group, that is this CH group correspond to this group. Okay. this is the oxidation product of quinine. This is the actual structure of quinine. Then the structure of this structure is further confirmed by the total synthesis of quinine. Then the synthesis of quinine. So it starts from 3-hydroxybenzaldehyde, and it condenses this molecule to form this heterocyclic ring system. Then it condenses with formaldehyde and piperidine to form this. That is, in case of formaldehyde, the CH2 group is come from this formaldehyde, and this ring is this E7H11N. Then it is treating with sodium methoxide at 250 degrees Celsius, and this bond is ruptured, and we have a molecule like this. Okay, there is also a double bond here. Okay. Then it is again reduced by H2PT, that is in catalytic in hydrogen in presence of catalyst. This ring is reduced, and the reduced ring may contain an H group. This H is protected by using it is heated with acetic anhydride, and this H is replaced by COCH3. Then again, the ring is another ring is reduced using our hydrogen and Rani nickel. Then it is oxidized, so the OH group is oxidized to ketone. Then this is actually an optically active compound, so the both form will be the the one of the form optically active form is separated. As in case of as for the synthesis of quinine. Okay, this is one of this is plus or minus form. This is a optically pure form. Okay. Then this is treating with ETO or NO complex, and in presence of sodium ethoxide. Then this bond is ruptured. This bond is ruptured, and we have a molecule like this. Then it is again reduced with hydrogen in presence of catalyst, and have a molecule like this. This molecule can also be write like this. That is N COCH3 COO C2H5 NH2, then CH3. So this group is CH, NH2, CH3 is here. Then the 6-membered ring is writing like this. Then COCH3 is here, and this CH2, CH2, COH is here. One more CH2 is here. Okay. Here is a CH2 group. Okay. CH2, CH2, COOH. You understand? I will write it one more and continue the reaction. That is, our molecule is COO C2H5 then nitrogen, the substituent of nitrogen is COCH3. Then there is an NH2 group and CH3 group. Then this molecule is treated with the CH3I. CH3I in presence of K2CO3. Then it is again hydrolyzed KOH and heat. Then this group is hydrolyzed, and this is converted into there will be an elimination reaction. Okay, that is Hoffman elimination. COOH and this bond also hydrolyzed. We have NH. Here first it become a quaternary ammonium salt, then elimination take place. Hoffman elimination, less substitute product will be the major product. Okay, then it is treating with the ETOH, ethanol, and COCl, benzoyl chloride. This hydrogen is again protected with this group COOH and COPH. CH double bond CH2. Okay. Then this part will be what part? Mirror quinine part. So we should have a quininic acid part. That is another molecule. OCH3. COOET. This molecule react with one more step is the COCH3. Okay, this is converted into ethanol. That is here first of all it is COH is converted into corresponding ester by using this ethanol and HCl. Then this nitrogen is protected as COPH because while other reaction there may be interference of the reagent here. That is why that secondary nitrogen is protected. Okay. So this compound will react with this one, that is COOET and again like writing like structure above structure COPH CH double bond CH2. Okay, in presence of NaOET, sodium ethoxide. These two compound condenses, that is this ester and this ester part will condense to form the molecule like this. Here is a nitrogen, here is an OCH3 group. Then here the product of condensation C double bond O group is formed. Then here is the point of attachment. That is the CH2 group of this will attack at this carbonyl carbon. Then OET group is eliminated. That is actually happening. The remaining portion COOET. COPH. Then again this group. Then CH double bond CH2. Then it is treating with the HCl hydrolysis. HCl. Then when it is hydrolyzed using HCl, this group is hydrolyzed, and when it is heated, a molecule of carbon dioxide is eliminated. COOH is eliminated. So this group is ruptured. Then eliminate a molecule of carbon dioxide. Then this is an optically active form. So one of the form is resolved. So this group is eliminated by hydrolysis followed by decarboxylation. So the product will be like this. OCH3, then here C double bond O, nitrogen. Then when it is hydrolyzed, this group is also hydrolyzed. Okay, NH CH double bond CH2. Okay, plus isomer is taken. Then we should attach these two groups by using NaOBr and followed by reaction with the NaOH. So this hydrogen and this will combine and form a closed ring. OCH3, C double bond O, CH double bond CH2. Okay, it is also saturated. This is actually plus quinine. This quinine, the difference between quinine and quinine is here double bond O. In quinine, there is OH group at here. So it is treating with the C2H5 OH. So this double bond O is reduced using this reagent. This reagent you will be familiar with. Then we have plus or minus quinine. Then after resolution, we have minus quinine, which is the naturally occurring quinine. That's about the structural elucidation of